This is the advanced rendering ACW video for Michael Oakes. Before I demonstrate the application, here are the available keys for use. Here is the terrain in desert mode. I create the terrain in the tessellation stage using 4 vertices in the far corners of the scene to form a quad. I apply a displacement function in the domain shader to create the terrain height and set a different colour in the pixel shader based on that height. Pressing C will take the scene into cartoon mode, which better highlights this. The height can also be adjusted up using the J key and down using the M key as shown. I create 2 sets of pillars in the scene. One set are the 3 holding up the roof on the right, created through tessellation in the domain shader from a parametric equation. The second set are the other 3 left roof pillars and the far left monumental pillars, which were generated through ray marching and blending. The soldiers, which are shown here, are created by the geometry shader, which uses 108 vertex points passed as a center point to generate a quad for the soldier. The 4 vertices are calculated as offsets from this point, with a factor included for size adjustment. To implement billboarding, the vertices are adjusted based on a normal, up and right, calculated from the camera position stroke look direction. The soldiers are textured from a shader resource. There are 2 flags in the scene, the textured Wakanda flag, shown here, and the coloured flag, shown here. The geometry shader uses 10 supplied vertex positions to create 8 triangles that form the flags. The flag is animated by adjusting the vertices on the z-axis, forward and back, using time, a sine function against x, and 3 adjustment variables. 1,000 programmatically generated points are used to create the clouds that are shown at the top here. The geometry shader creates quads as offsets from these points, billboards them to face the camera, and textures them from a shader resource. Time is used to adjust the X position to create the drifting effect, with a random function and SV primitive ID used to readjust and spread out the clouds and prevent bunching. Ray tracing is used to create the checkerboard cube shown here, with 6 quads used to create each face. I intersect check against these faces, returning the ray hit point to create the cube. The fractional part of a mod floor calculation against the axis for each face determines the positions for the black and white checks. Spheres are created from a center point and radius, with a sphere intersection test against the ray, returning a hit point to create each sphere. I create 3 smooth set blended objects in the scene using ray marching. Firstly, an Easter Island head, shown here, created by blending 2 elongated spheres, a pyramid for the nose, and 2 new spheres for the eye hollows. A combination of smooth and hard unions and differences blend the shapes together. Secondly, a rotating tulip shape here, created by blending a cylinder, a pyramid, and a rotating sphere using both a hard and soft union with an onion effect to change the final appearance. Finally, a cube, here on the left hand side, that deforms on collision with animated spheres. I create 3 animated spheres that intersect with the cube and use a combination of smooth unions and smooth different blends to create the cube deformity. I only make 2 of the spheres visible in the scene. I created a set of infinite simple coloured shapes, pyramid, torus, sphere and cube, using ray marching with blended parametric equations shown here on the right hand side of the scene. To stop the scene becoming too cluttered, I restrict their position to over on the right hand side, and the raised terrain and far points obscures the view of the objects that are further out. In the tessellation stage, I use parametric equations in the domain shader to generate the set of solid stone artifacts, ellipse, sphere, octahedron and torus shown here at the bottom right. I use the hull and domain shader to generate patches and create the objects. I manipulated and adjusted the sine and cosine from the sphere equation to create this vase-shaped object. A bumpy rock is created in the scene from an octahedron parametric equation in the domain shader, shown here on the left-hand side as both solid and wireframe. It is created using the hull shader tessellation factor, displacement mapping and MIP levels. Tessellation factor is set in the hull shader through the constant buffer and can be adjusted down using the G key as shown here, and then up using the T key as shown here. Likewise, the bump height is supplied to the domain shader in the same way, and the displacement height factor can be adjusted up using the H key and then down using the N key. As you can see, this takes this back down to an octahedron. The rock from effect 5.2 is rendered twice more in the scene, here as wireframe and here as solid. It is generated as before, however the tessellation factor is now calculated in the vertex shader based on the rock position from the camera and then passed to the hull shader. The tessellation factor increases when the rock is moved nearer to the camera, demonstrated here by pressing the R key and bringing the rocks closer. It then decreases when it's further away from the camera, as demonstrated here by holding down the E key and moving the rocks further away. I created 4 free-form objects in the scene based on spline techniques. I created a curved roof, shown here, a Mayan temple, shown here, and 2 instances of the Utah teapot, shown here and here. For the roof, temple and purple teapot, I used bicubic interpolation of B-spline Bezier curves, calculated using the de Castelgiao algorithm with 16 control points, and then for the red teapot I used Bernstein polynomials. The control points for the 3 temple sections and the roof are created programmatically in the domain shader, and the temple sections have a low tessellation factor to keep them square-edged. The spline objects can be toggled between solid and wireframe mode using the B key as shown here. I utilised a ping-pong rendering approach to create realistic 3D by properly blending ray tracing, ray marching and the geometry tessellation effects. Render textures are used to merge the different techniques and preserve depth in the scene. The ray tracing, ray marching scenes, colour and relevant depth are drawn to 2 render textures. I then draw the geometry tessellation, colour and depth values to 2 other different render textures. A pixel shader is then used that references all 4 textures, compares the depth and colour textures, discarding anything with an alpha close to 0, drawing to the back buffer the colours and depths of the objects nearing the camera stroke eye. I tried to implement grass using a geometry and tessellation shader and billboarding, but I ran out of time to complete this. It is disabled in the scene, but the code for it can be found in the Novelty GS geometry shader.